Hello, I am Ilma. Today we will talk about numbers other than integers. Among the numbers used in everyday life, floating point numbers are the second most used number in programming after integers. Many programming languages support only integer and floating point numbers as numerical data, and in such languages all numbers that cannot be represented as integers are represented as floating point numbers. An obvious example of a floating point number is a number containing a fractional value. Let's enter some s expressions. -0.2 3.14 1,003.8. Evaluating the input s expressions returns floating point numbers that have the same appearance as the s expressions. When you enter an s expression representing a floating point number, Viivi reacts in the same way as it does with integer values. The general expression for floating point numbers is explained with an example. The number 2.71 is a floating point number, which, when multiplied by 10, becomes 27.1. Multiplying by 100 gives 271.0, by 1000, 2710.0, and so on. The digits of the number 1 are aligned on the screen. On the other hand, 2.71 multiplied by 0.1 gives 0.271, and by 0.01, 0.0271, and so on, as shown on the screen. If the multiplying factor is written as it is, for example multiply by 1000 or multiply by 0.001, the digits will be too long, so in mathematics, exponential notation is used. The exponential notation, corresponding to 10, 100 and 1000, can be written to the right, as 10 to the power of 1, 10 squared and 10 cubed respectively. Using this exponential notation, the part after the multiplication sign can be shortened. The same can be done for larger numbers. Similarly, 0.1 is 1/10, so 10 to the power of -1, 0.01 is 1/100th, so 10 to the power of -2, 0.001 is 1,000th, so 10 to the power of -3, etc. If we rewrite the values on the smaller side than the original numbers, we can write them as on the screen. 2.71 itself is 2.71 by 1, but 1 equals 10 to the power of 0, so the exponential notation for 2.71 is 2.71 by 10 to the power of 0. Exponential notation is convenient because it can be written in short sentences. However, in program code, it is not possible to write the exponent in a small font. We therefore write en to multiply by 10 to the power of n. Even if n is a negative number, it is not enclosed in parentheses. In this exponential notation, each number is written as shown on the far right. When a number is expressed in exponential notation, the latter part, that specifies the digits, is called the exponential part. On the other hand, the sequence of numbers, ignoring the digit specification by the exponential part, in this case only 2, 7, 1, is called the significant digits. In exponential notation, the part indicating the significant digits, is called the mantissa part, and for numbers other than 0.0, there is a rule to specify a range, 1.0 or larger, and less than 10.0. By following this rule, for a given number, the mantissa part and the exponent part are determined in a unique way, and, therefore, the entire exponential notation is determined in a unique way. If you display the significant digits in the usual notation, for example, with the digit 1 aligned as shown on the screen, you can see how the decimal point changes its position, as if it were floating, whenever the value of the exponent part changes. The curious name, floating point number, is derived from the fact that the position of the decimal point appears to float, when only the value of the exponent part is changed. This exponential notation is common and widely used, not only in Scheme, but also in many programming languages and spreadsheet software. When entering floating point numbers as S expressions, you can use either normal or exponential notation. However, when the value is output as an evaluation value, the notation that is easier to read is automatically chosen. For example, in my environment, when the above example is output as an evaluation value, it is displayed in normal notation, from 0.00271 to 2,710,000.0, and in exponential notation, in the range outside that. Let's look at examples of exponential notation for floating point numbers. Enter the S expression of a floating point number, with a large number of digits, in normal notation. It is displayed in exponential notation. If the value is very small, it is displayed in exponential notation. Next, try entering the S expression in exponential notation. This is output in exponential notation. Try changing the value. This is output in normal notation. If the notation of the input S expression is not correct, but Viivi can recognize the value, she will correct it to the correct display format and return the value. For example, a decimal number starting with a decimal point. Correctly recognized. There is no problem if the mantissa or exponent part is marked with a plus sign. If the mantissa is 10.0 or greater, or less than 1.0, it is still recognized correctly. Of course, S expressions that cannot be interpreted as floating point numbers will result in an error. For example, try to give a floating point number for the exponent part. Viivi cannot understand it, and an error occurs. The floating point numbers that can be used in Viivi are double precision floating point numbers, with a length of 64 bits. The range of these floating point numbers is 0.0, and the two ranges shown on the screen. All values between these two ranges are treated as 0.0. With floating point numbers, the wide range of numbers can be handled with a fixed amount of memory of 64 bits. On the other hand, the disadvantage is that the number of digits near the end of the significant digits may contain an error called rounding error. This is due to the fractional part of the mantissa being represented by binary numbers that use only a limited number of digits 0 and 1 internally. However, because Viivi floating point numbers have about 18 significant digits, such errors are rarely a problem. Most programming languages only support two types of numerical data, integer values and floating point numbers. In addition to these, R5RS includes descriptions of fractions and complex numbers. Furthermore, there are a number of prefixes that can be written in front of S expressions representing numerical values. This makes the Scheme language highly expressive for numerical values. Fractional and complex numbers, and prefixes, can also be used in Viivi. However, they are not used at the introductory level. We have omitted all of them here, as they would only confuse you. We will explain them whenever they become necessary. If you want to know now, please see our 5RS directly. Although we have shown that many different types of numbers can be used, in general, only integer and floating point numbers are commonly used as numerical data. In so-called system programming, which is purely concerned with the internal components of the computer, CPU, memory, files, etc., only integer values may appear in numerical data. On the other hand, in scientific and technical calculations that process data from the world outside the computer, in graphics and in games that represent the virtual real world, floating point numbers are treated as the main type of data. This concludes our discussion on numerical data. Thank you for watching this video. In the next video, we will look at strings, which are as basic as numerical data. See you next time. To continue learning, please subscribe to the channel by clicking the subscribe button. Thank you.